So we'll talk about PRGs, specifically fractional PRGs, which we will define next. And during this talk, I always work with functions from ±1 to ±1. Will be more convenient. And recall that we have the Fourier decomposition of such functions. We can write every function f of x as some yes like x overall s subset of 1 to n.
Also above is minus plus minus 1 to the n.
Plus minus 1 to the n. Yes. Okay, and this is called the multilinear extension of the function f. And the reason it is called an extension of f is because in this form we can also plug inputs that are not plus or minus 1. We can plug any real or even complex number that we want. Okay, so in this talk we'll plug x in -1, 1 to the n. Inside the Boolean cube, not only on the corners of the Boolean cube. And how should we think about f of x? I mean, if we plug in a fractional input, how can we think about f of x in terms of the original function f? So it's the same as defining pi x, which is a distribution on the Boolean cube. Such that, okay, so let's draw the Boolean cube. And this is 0 to the n. And in each coordinate, let's say I plug in this coordinate. So this is like 0 in the x coordinate and 1/2 in the second coordinate. So it's equivalent to not to choose whether I go left or right, whether I go to -1 or plus 1 in the x coordinate, but to prefer going to 1 over -1 in the y coordinate. Okay, so pi x in the coordinate I. So pi x is a distribution of vectors. And when I look at the I coordinate, the expectation of this is simply xi. And I define pi x by this relation. It's the only product distribution with this property. Okay, and you should think of it as if we plug a point that is close to 1 in the say in the y-axis, in the x2 axis, then with high probability I'll plug x2 equals 1. And with low probability I'll plug x2 equals -1.
What is pi again? What's it?
So pi x is a distribution. It's the unique product distribution that satisfies this relation. Okay? And now f of x, plugging a fractional point, can be thought of plugging the distribution pi x, which is distributed on the corners of the Boolean cube. Expectation over expectation of okay. And why is this true? Because we take a product distribution and then the expectation jumps in. Okay, clear? Let's write it. Sum S product expectation by x by right. This is just taking the expectation, and this is just xi, right? So plugging a fractional point can be thought of as plugging a distribution on the true points in the Boolean cube. Okay, so what does plugging 0 to the n mean?
Taking the uniform distribution.
Taking the uniform distribution, right? You can see it in several ways. In this drawing, you can say, I don't tend to plus or minus 1 with larger probability, it's just uniform. And here you can see that you plug 0 to the n, so all the terms vanish except of f hat of the empty set. And okay, so let's write it. F hat of the empty set. And what we want from a fractional PRG, we want to, okay, so S is a fractional PRG. If it fools F, no, but we allow S to be fractional, containing minus 1, 1 to the n, the interval minus 1. Is a fractional PRG if with epsilon, if expectation of f of s minus. So let's write it as f of 0 to the n is smaller than s. Okay, so here we sample uniformly from S. I think of S both as a set and as a random variable that uniformly samples from that set, as always. So this is a fractional PRG, and we already have a perfect fractional PRG. And so what's the point of this fractional PRG? Is that with some conditions, which will not allow S to be 0 to the n, we'll have a way to construct regular PRGs from fractional PRGs. Okay, so these are used to construct real PRGs. So what's the condition? So it's called noticeability. So the condition says that we need to have some variance in each coordinate. So x and minus 1 to the n is q noticeable if station xi square is larger than q for all I. Okay, so each of the coordinates has enough variance. Okay, so our previous PRG, which is just 0 to the n, is 0 noticeable. It's not even 0 noticeable. No, it is 0 noticeable. But it's not going to help us at all. What we are going to prove now is okay, so this is the main theorem. So f is a family of functions from 0, 1, from plus minus 1 to plus minus 1 as before. Okay, I won't write it. F is as always and is closed under restrictions and shifts. We'll see it in the proof, and we'll see what we exactly need from F. What I mean by is closed under restrictions. I don't want to.
Similar to the previous.
The shifts are similar to the previous talk, and here we also need the closure under restrictions, which we'll see later on. And suppose X is Q noticeable. Notice the and rules F with arrow epsilon. Seed length S. Okay, so we have a family of functions, and we have a fractional PRG, a Q noticeable fractional PRG that fools F, and we can construct a new regular PRG that fools F. So there exists a PRG, regular PRG, fools F with arrow epsilon over Q times log n over epsilon. Okay, so we lose a factor of Q and a factor of log n over epsilon. And the seed length also had the same loss. S over Q times log n over epsilon. Okay, so is it clear? So we'll now describe the process, the construction of this PRG, and later on we'll prove that this construction works. So it's going to be an iterative construction, and we are going to use T copies of the fractional PRG. And so we start with y0 equals 0 to the n. We start here with a perfect PRG. Then we add a copy of x. So assume x is like fractional. It has some points inside in the Boolean cube. Okay, so I'll describe not the whole set, but the way I sample a point from the PRG. Okay, so I start with a copy of x and I sample one point from it. Okay, and then I'm going to take another copy of x starting from this point. Okay, so I'll have it, I mean, I can forget about these. And I have another copy of x at this point. Okay, and then say I choose this point. I'll have another copy. So you can see that if I take too many steps, I can choose points that go out from the Boolean cube, right? Because so we apply a trick and we scale x whenever we take another sample. Okay, so if I'm standing in this point, I won't sample x because I can't get a point that is here, but I scale x to be in this regime. Okay, so formally let's write it. y0 equals 0 to the n. Y plus 1 equals, so it's yi plus delta yi pointwise multiplication with x I plus 1. Okay, I need to explain this term, but this is going to be the normalization. Okay, so we take the previous point and then plug another copy of x, but normalized accordingly. So what's delta? Delta y in I coordinate equals 1 minus sine y. Okay, so I normalize each coordinate separately. So if I had a point here, I'll scale the first axis, and so we'll have something like that. Okay, a scaled version of x, which is shrink in the first axis and a little less shrink in the second axis. And okay, and this is just pointwise multiplication. Okay, why is this good? So one of our claims will be that in this way we converge quickly to points that are close to the corner of the Boolean cube. Okay, why is that? So everything works perfectly on one axis and generalizes to multiple axes. So let us think of one axis problem, and say we have a random variable x that takes us either right or left, and say we took the first step to the right, and then we use a shrinked version of x, right? So say we now took a left step, we are still a little more right than we were at the beginning, okay? So if you think of a walk that is right, left, right, left, right, left, you will converge to the edge, okay? And generally this is what's going to happen. So we'll prove now, we'll state 3 claims and prove 2 of them. Okay, so 1, each step, in a step I mean moving from yi to yi plus 1, each step introduces small demo. We converge quickly. And 3, condition on convergence. So condition that our fractional PRG is very near the corners of the Boolean cube, we can simply round the points to an integer point, and the rounding doesn't help the error of the PRG too much. Condition on convergence, rounding doesn't help too much. Okay, so let's make these quantitative. Each step introduces a small error. Okay, so expectation of y plus the expectation of f evaluated on 1 y plus 1 minus expectation of x evaluated on 1 yi is smaller than epsilon. We converge quickly, so So after t steps for t to be determined later, the infinity norm of delta is really small, epsilon, and probability 1 minus epsilon. And then for this, we need t equals omega of log n over epsilon over q. Okay, so this is you can see the seed length. This is the same quantity that appears here. This is q. And condition on convergence, rounding doesn't help, so expectation of, can you see this? F yt minus expectation of sine yt is smaller than epsilon. Okay, and so we'll prove 1 and 3, and you will be listening for the second bullet. And then if we have time, we'll pack everything together and prove that these lemmas give us the theorem. Okay. So let's write this one. So let's fix yi. We'll show something stronger, that for every fixed y, f of y minus f of y plus delta y times x, expectation over x, is smaller than epsilon. Station should be here, but I think it's the same. Okay, so let's define random restriction in a point y. So what's a random restriction? Did we talk about it in this class? So what's a random restriction?
We just put some constants instead of the variables.
So in some probability, you fix, so let's say you have yet to be determined vector x that is sampled from x. But now you choose some coordinates randomly and fix some of them randomly too. Okay, so let's say a random restriction may choose these coordinates and plug 1, 1, 0, minus 1. And then here you sample x2, x4, x5. You don't touch these variables. Okay, so this is a general way to describe random restriction. And we'll specify the random restriction that we need for our needs. So if we get a vector x, and we randomly restrict it with the random restriction corresponding to y, look at the I coordinate, is so the survival probability of xi is 1 minus the size of yi. And else we plug sign of yi. Okay, so this is not the random restrictions that we usually think of. So if we were in a point here, so 1 minus the size of yi is really small. So the variable survives with a very small probability, and with high probability, we just fix it to the corner. Okay, and what's the expectation over
It's not necessarily the corner, right? It can be the side.
Yeah, so we separate the coordinates. So if we're in a point here, so we're very likely to be to collapse to this edge, but not to collapse to any of the corners. So the expectation over r, ry, and x, say in the ith coordinate, is so I think it should be this is just y plus delta y times x. Okay, and this is just working out the expectation. You get this because 1 minus y is just delta y. Okay. You can do it for a single coordinate. Let's do it. So the expectation of r, y composed with x on the ith coordinate is, so it's minus yi times xi plus value of yi times sine of yi. I think this is just yi, right? The absolute value times the sine. So this is yi. And this is just delta y I. So taking all the coordinates at once, we get this. Okay, why does this help us? So I'm now erasing the f must be closed under restrictions, and now we are going to see why this is important. Okay, so let's write expected value of f of y minus expected value of f of y plus delta y x. So this is not really an expectation, right? This is just f of y. There is nothing to take expectation over. But this is the same as expectation over r of f somehow of 0 to bn minus expectation of f of y of okay, because randomly restricting is the same as taking this And if we plug 0 to the n, this term vanishes and we just get y. And if we plug x, we simply get this. This is a capital X. Okay, agree so far? Questions?
I'm not following all the details, but I think I get the idea.
Okay, so why is this smaller than epsilon? So this is just, as we know, f pad of the empty set, f sub ry, and or f sub ry on the uniform distribution, right? It's all the same, and this is x plugged into f restricted to ry, and as we said that the class f is closed under restrictions, and x fools f, this must be smaller than epsilon. Okay, so this is really the condition we need. We need that this term is smaller than epsilon. This is actually a little weaker than f is closed under restrictions. We need that on average, x fools f on random restrictions. Something like that. Okay. So we proved the first lemma. The second lemma is not very insightful, so I'll skip it. But the main point is that we need to perform t steps in the fractional PRG, and t should be logarithmic in n and the epsilon, and inverse linear in q. And this suffices for this condition to hold, which is very strong. We'll be really close to the corners, like epsilon over n in the infinity norm, with very high probability. Okay, so these random walks, the one we described before, converge really fast. Okay, they get really close to the corners with very high probability. And we only need t equals omega of log n over epsilon steps. Okay, so let's move to the third bullet. Any questions?
Meaning the Q not is available for step 2.
Yes, I think so. Otherwise, you won't converge. You can have a fractional PRG which is just 0 to the n, and you will step in your place. Okay. So say we're really close to the corner in a Boolean cube, and now we want to evaluate f on the corner and compare it to f really near the corner. And recall that f of x is equivalent to expectation of f of pi x. Okay, so you remember this? So if we are in a point here, we can think of it as sampling from a distribution which picks the corner point, the relevant corner point, with very high probability, right? Okay, so what's the probability that pi x is not equal to the sign of x as a vector. Okay, so this one samples a vector and this one is a vector. So the probability to um, uh, not to be equal on the first coordinate should be 1 minus xi over 2. Why is that? Sum over I. So maybe I should say, I should write ix in the I coordinate equals plus 1 with some probability and minus 1. And I think and we want so this is p and this is 1 minus p, and we want expectation of pi x in the I coordinate equals xi, and I think the suitable p is 1 minus side of xi over 2. Right? Because what is this? This is p pi minus 1 minus pi equals 1 minus 2 pi. Equals xi. That's what we want. So we get 1 minus xi over 2. And I probably missed I'm missing something with the absolute value, but you should believe me that the probability that in the ith coordinate pi does not equal to the sign of xi is equal to this term, and then the union bound just gives us the sum of all the coordinates. נסיים עוד 10 דקות, בסדר? אין בעיה. Okay, so what's the probability that f of y doesn't equal to the f of sine of y? Maybe instead of y, let's write yt. So let's, and the lemma says conditioned on convergence. Conditioned on the convergence is stated here. The infinity norm of yt is really small. So this is at most 2 times the probability that pi yi yt doesn't equal to pi 2 sine of yt. Okay, because we divide the cases with the probability, how do you call it in English? הסתברות שלמה. Yeah, the probability you get this found. I mean, you condition on y to the t equals to the sign, and condition on the other case, and you get this. And this is at most. So each one of these terms is at most epsilon over n, and we have n summands, right? And the two cancel with these two, and this is at most epsilon. Okay, so let's write it. It's 2 times sum 1 minus y the t in the I coordinate over 2, and this is at most n summands times epsilon over n, which is this one, equals epsilon. Okay, so let's put everything together and finish. Okay, so our final PRG is sine of y to the t. Taking f on this term, or taking f on so just taking the expectation over this term, and taking the expectation of f of u, right? That's what we need. And this is more or equal to expectation of f of u minus expectation of f y t plus expectation of f of y of t minus expectation of f sine of y to the t. The absolute value. Okay, and this one, okay, are you okay with this step? This one is at most epsilon because of the third rule, right? Okay, so let's continue with this. So here we use a hybrid argument, I guess, is at most. So we plug in between expectation plus minus expectation of f of y to the I, right? And this is at most. So we have t steps, and each one of them, in each step, we introduce an arrow of at most epsilon. What am I missing? Oh, so here. Okay, so this is true. This is at most t times epsilon, but here we need to condition on the convergence. Okay, we said that conditioned on convergence, this is smaller than epsilon, and we have that with high probability we converge. So this term is expectation of blah 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 conditioned on convergence times probability of convergence, and this one is expectation of blah 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 convergence complement times the probability of not converging. Okay, so this one is at most epsilon, and this one is at most 1. And this one is at most epsilon, and this one is at most 1. All in all, we have at most t plus 2 epsilon. Okay, so our new PRG pulls the family of functions f with this term, as we stated in the beginning.